Today, we will presenting to you a segmentation approach for detecting human retina based on optical coherence tomography data. Especially during this presentation, we will show how to segment volumetric data and achieve additionally labelings which respect the biological retina layer order. For this purpose, we equip a set of probability simplices with Fisher-Rao geometry and achieve special regularization through geometric averaging of the data by integrating a dynamical system on the statistical manifold. Additionally, we explain how to constrain the assignment manifold to lead order preserving labelings, which provide our approach with a modelable structure for applying it to segmentation of pathological datasets and without introducing any bias as opposed to incorporating a shape prior.
Welcome to our project on boosting generalization in biosignal classification by leveraging the phase amplitude component. When it comes to biosignals, annotated data is expensive, the labels can be noisy, and the data itself contains large amount of variability. Instead, we choose to learn useful feature representation through self-supervision, where we train a neural network on an artificial task for which labels can be generated automatically. Our main contribution is the phase swap self-supervised task, where we train a network to discriminate between real samples and samples for which the phase information in the Fourier domain was swapped out by one taken from another sample. We show on multiple datasets that the features obtained this way are more robust to changes in experimental settings and subject identities compared to a supervised baseline. For more information, tune in to our oral presentation and check out our project webpage.
Hello everyone, in this work we address the important problem of long-tailed recognition using an ensemble of class-balanced experts. Our simple and effective strategy decomposes the long-tailed dataset into approximately balanced subsets of many shot, medium shot, and few shot data. We then train an expert model for each subset. We add a region class to each expert classifier to separate classes from the other two subsets. The partial posteriors from the experts are jointly calibrated to produce a full posterior distribution from which we get the final prediction. Our ensemble of experts reaches close to state-of-the-art on two benchmark datasets, and an extended ensemble establishes a new state-of-the-art. Furthermore, our experiments with an upper bound using orbital access to the ground truth expert reveal that relative imbalance is a more severe problem than data scarcity. Hope to see you at the conference.
Hi everyone, welcome to our work, analyzing the dependency of CompNets on spatial information. In this paper, we aim to investigate the reliance on spatial information in image classification task. We propose to discard spatial information via shuffling locations or average pooling during both training and testing phases to investigate the impact on individual layers. As an example here, we have the architecture of the VGG16 on the left. In order to prevent the model from making use of spatial information, at each iteration during training and testing, we randomly shuffle the feature maps from the last half layers spatially. The training processes of a standard VGG16 and a shuffled one on CFAR 100 are shown on the right. Interestingly, the test accuracy only drops by around 2.6% and the training processes are nearly identical. This observation generalizes to various architectures and datasets. This indicates that spatial information is overrated for standard CNNs and not necessary to reach competitive performances. Thank you for your attention.
We are excited to present learning monocular 3D vehicle detection without 3D bounding box labels. Training 3D object detectors requires large datasets with 3D bounding box labels for supervision. We overcome the need for manual labeling. Instead of a bounding box, our model predicts the pose and shape of each vehicle. Through differentiable rendering, we define loss functions based on segmentation masks, depth maps, and photometric consistency. All inputs are generated by pre-trained off-the-shelf networks. We evaluate our model on Kitty and achieve promising performance in comparison to state-of-the-art methods, which require 3D bounding box labels, and superior performance to baseline methods. Please visit our project website for more information, and thank you for your attention.
Hi, my name is Morris, and I present the teaser for our paper Observer-Dependent Lossy Image Compression. If you compress an image, then often it is viewed by different types of observers, which can either be human or computer vision systems, such as image classifiers. The majority of research has so far focused on the human observer. In this work, we ask, can we optimize compression explicitly such that classification accuracy is maintained, and trade off compression quality between different types of observers? Our approach is based on encoding the observer in the loss function used to train deep image compression, using a human-inspired notion of similarity for human-optimized compression, and the feature reconstruction loss based on deep VGG features to train classification-centric compression. Our experimental results show that we can indeed optimize compression explicitly to preserve classification accuracy on compressed images, and that a trade-off between the two types of observers does exist. For more details, please see our paper.
Hi, my name is Morris, and I present the teaser for our paper Observer-Dependent Lossy Image Compression. If you compress an image, then often it is viewed by different types of observers, which can either be human or computer vision systems, such as image classifiers. The majority of research has so far focused on the human observer. In this work, we ask, can we optimize compression explicitly such that classification accuracy is maintained, and trade off compression quality between different types of observers? Our approach is based on encoding the observer in the loss function used to train deep image compression, using a human-inspired notion of similarity for human-optimized compression, and the feature reconstruction loss based on deep VGG features to train classification-centric compression. Our experimental results show that we can indeed optimize compression explicitly to preserve classification accuracy on compressed images, and that a trade-off between the two types of observers does exist. For more details, please see our paper.
In this paper, we propose a framework for anticipating activities with cycle consistency. We humans have a strong capability in predicting the future. Given a sequence of observed frames, we can predict the possible activities that may happen in the future. In this example, the person would add a tea bag and pour water into the cup. Moreover, our capabilities goes beyond anticipating the future. Given the future activities, we can also reason about the activities that happened before. In this work, we build a sequence-to-sequence model that simulates these two capabilities for anticipating a sequence of future activities with their durations. Our model achieves state-of-the-art results on two datasets. For more details, please refer to our paper.
Hello and welcome to our paper Multi-Stage Fusion for One-Click Segmentation. One-click segmentation refers to a typical image capture scenario where the user taps or clicks on the device touchscreen to select the object of interest. This selection click can be leveraged for segmentation and can be used for downstream applications such as background blur. In addition to conventional early fusion, we propose a new late fusion module. This reduces the layers of abstraction and allows user interactions to have more impact on the output. Here is our proposed multi-stage fusion framework. Here we look at masks generated using the early fusion and the multi-stage fusion module. We observe significant improvements in the quality of masks generated. We compare against competing methods in literature. We achieve state-of-the-art performance across 5 standard benchmark datasets. Thank you.
Hello, my name is Jovita Lukasic and I'm going to give you a short overview about the work Neural Architecture Performance Prediction using Graph Neural Network. In this work, we present a surrogate model to learn to predict accuracies of convolution neural architectures in a supervised way. For that, we use a graph neural network from the literature to map the graph data architectures into a latent space, which is then trained jointly with a regressor for different performance prediction tasks. We can see in Table 1 the traditional supervised setting as well as the zero-shot performance prediction compared to different baselines. Furthermore, we can see that our GNN is able to predict the performances in a stable way and also outperforms all baselines. Furthermore, these experiments examine the various capabilities of our GNN encoder for performance prediction, making it a powerful tool as a surrogate model. I hope that it waked a little bit of interest and we will see us in the live session. Thank you very much for listening.
Hello, I'm Olga, and I'm happy to present our work on Latin classes discovery for semi-supervised semantic segmentation. Existing semi-supervised approaches focus on harnessing such regions of unlabeled images that are easy to segment, and thus large parts of images get discarded during training. In this work, we propose an approach that does not discard any information. We learn a simpler segmentation task and then use it as additional guidance to solve the original task. To this end, we introduce a two-branch model trained in the end-to-end fashion. While semantic branch solves the original task, the purpose of the Latin branch is to discover Latin classes that are simple enough to be learned accurately on a small set of labeled data. Then we use Latin branch to get additional supervision for the semantic branch on unlabeled images. Our model achieves state-of-the-art results on two major semantic segmentation datasets for different labeled data fractions. We also show that discarded Latin classes have an intuitive meaning, since they learn to group semantic classes into supercategories based on similar appearance. Check out our paper for more details. Thank you.
Assume we want to model an arbitrary data distribution in terms of an elementary reference measure. A current prominent line of research concerns the representation and estimation of so-called normalizing flows. We want to focus on a special kind of normalizing flow, the so-called Nord-Rosenblatt map. This class allows for good invertibility. Therefore, a solution to the inverse problem also yields a solution to the original problem. We consider a polynomial basis in each component of the transport map. For this purpose, we focus on so-called SOS polynomials, which can be identified with the cone of positive definite matrices. This yields a canonical parametrization that ensures bijectivity. We can now introduce a proper geometry on the cone and derive two different flows which take this geometry into account. More details will be shown in the corresponding talk as well as in the paper.
Hello, I'm Remy Vandel from the University of Reading, and I'm going to summarize my work on using transfer learning for semantic water segmentation. To be clear, our goal is to create a method that is able to automatically generate a watermask of a natural RGB image. This is especially useful in the context of river monitoring and flood modeling. We tackle the problem by applying transfer learning on state-of-the-art semantic segmentation networks that were trained on large datasets of natural images. We realized our experiments on two different water segmentation datasets and found out that our transfer learning approach could outperform the current state-of-the-art methods. Of course, if you want to know more, I invite you to read our paper and attend our 5-minute presentation.
Does stochastic gradient descent implicitly optimize for smoothness? Neural networks do not overfit, even when their capacity is so high that they reach zero training error. A common explanation is that SGD is implicitly biased to select functions of low complexity, which generalize well. But it is unclear what complexity is exactly and how to measure it. We explore the hypothesis that the complexity that SGD optimizes for is smoothness, meaning that it tends to learn functions that are not too bumpy. To determine if this is the case, we designed ways to measure smoothness and conducted experiments to verify the hypothesis. The design of the experiments is general and could be used to examine other complexity measures as well. We managed to reject the smoothness hypothesis for measures of smoothness based on first derivatives. On the other hand, the results were promising for measures based on second derivatives, such as curvature.
Hello everybody, my name is Ronny Hensch from the German Aerospace Center, and the topic of my talk is how important context is in the semantic segmentation of pulsar images. SAR is an active sensor that records the echo of a microwave pulse backscattered on the ground. Increasing the context means that the classifier has not only access to the information that is contained in the spectral signature in one single pixel, but also to texture, shape, or information in a larger neighborhood. We use projection-based random forest as they can be applied directly to the complex value data of the pulsar images, and furthermore, they give us a direct control over how much context the classifier actually has access to. We apply our method to two pulsar datasets, one airborne dataset over a rural area and one spaceborne dataset over a dense urban area. And we show that by including context, at least to some extent, we can improve the classification accuracy significantly.
Welcome to our talk on Haar wavelet-based block autoregressive flows for trajectories. I am Apratim Bhattacharya, and this is a joint work with Christoph Strele, Mario Fritz, and Bernd Schiele. Prediction of future pedestrian trajectories over long time horizons is important for the success of autonomous agents like self-driving cars. In this work, we propose a novel normalizing flow-based exact inference model using Haar wavelets to effectively capture the multimodality of pedestrian trajectory distributions. Our HBA flow model consists of k coarse-to-fine scales. Haar wavelet-based transformations are applied at each scale to obtain downsampled coarse and fine components. Normalizing flows at each scale are block autoregressively conditioned on coarse trajectories which provide global context for the subsequent finer scales. Experiments on the Stanford drone and intersection drone datasets show that our HBA flow model can effectively capture the distribution of likely future trajectories. This is reflected in the accuracy metrics where our HBA flow model outperforms the previous state of the art. Our HBA flow model can thus better capture the modes of the trajectory distribution.
Hi, my name is Isabel Hofstetter, and I'm pleased to present our paper Constellation Codebooks for Reliable Vehicle Localization. Localization is a safety-relevant task, and therefore integrity requirements have to be met that guarantee correct positioning. In our eyes, the key to integrity of localization lies in the reliable association of detected with mapped features. An example map containing cylindrical localization features is shown on the lower left. In this work, we propose to identify and extract feature patterns from maps which fulfill certain uniqueness requirements. These are encoded and stored in a so-called Constellation Codebook. At the same time, we try to exclude ambiguous patterns that would risk correct data association. Online, instead of the entire map, only the Constellation Codebook containing all unique encoded patterns is provided for localization. Under certain assumptions on sensor faults, we can now guarantee remaining error rates for feature association.
In this work, we present a flexible panoptic segmentation network that uses a bottom-up approach and call it Bounding Box Free Network or BBFNet. Panoptic segmentation is an ideal problem for using proposal-free bottom-up approach as it already requires per pixel semantic class labels. We use this observation to exploit class boundaries from off-the-shelf semantic segmentation backbone networks and refine them to predict instance labels. For refinement, we use intermediate stages for Huff voting and watershed level predictions to detect instances of different scales and combine these coarse predictions with a triplet loss stage. Using this approach, we outperform existing proposal-free methods on the popular COCO Panoptic Challenge. For more information, please attend.
In our paper, we propose an instance segmentation method and apply it to 3D neuron segmentation, which is a task where every neuron should be assigned to a distinct label. For each pixel in the image, our model predicts binary segmentation masks of the instance associated to the central pixel. Instead of directly predicting masks for every pixel in the image, we train our model to predict them in a compressed latent space, and save in this way a lot of computations and memory. As a result, our model predicts multiple values of instance affinities for a given pair of pixels, one value for each associated mask. We then also propose a method to aggregate these values and quantify the uncertainty of the final aggregated prediction. A graph clustering algorithm is then used to output the final instance segmentation.
In recent years, we have seen a lot of work on unsupervised keypoint learning. For example, from Jakob et al., from Zhang et al., and from Lawrence et al. These methods work great for keypoints, but they don't scale well to segmentation problems, even with CRF post-processing. We thought, can we do something different? And we had an idea. Our method introduces path segmentations as latent variables in a generative model. Doing so, we can build a method that works pretty good on deep fashion, exercise, and pen action. The method also works to some extent on the cupbearer dataset. We can do some cool stuff like path-based appearance transfer. Here we incrementally increase the amount of paths being transferred. Quantitatively, we show an improved segmentation performance in terms of IOU and an improved shape consistency in terms of PCK. Thanks for watching, and please check out our project page.
In this presentation, we're going to talk about the following tree partition problem. Given a tree T and real valued costs for each pair of distinct nodes, we want to find a partition of T that minimizes the sum of costs for all pairs that are in the same component. It is written as the minimization of a multilinear polynomial over binary variables, where each monomial corresponds to a path in the tree. We study the feasible set of an ILP formulation of this problem, which is equivalent to the lifted multicut polytope for trees. The name is due to its vertices being the characteristic vectors of multicuts of T lifted to the complete graph. In this paper, we characterize its elementary facets and present an additional class of facets associated with paths in the tree. We further show that the facets we discuss yield a complete description of the polytope if the tree itself is a path. For more details, you are welcome to attend our talk.
I am Linton Adesoni from the Visual Learning Lab in Heidelberg, and I'm presenting conditional invertible neural networks for diverse image-to-image translation. To summarize our method, we start by using a standard feed-forward network to extract the feature pyramid from the input image. We then show how to inject these features as conditioning information into an invertible neural network. This allows generating new images conditioned on the input image. We call the whole setup a conditional invertible neural network. Both components can be trained jointly, from scratch, using only one maximum likelihood loss. We see various benefits over other conditional models like CGANs. The model always gives the full diversity without mode collapse. The training is simpler, more stable, and more consistent. We have some theoretical results about the feature pyramid and the generated images. Also, the invertibility allows for some intuitive manipulations of images, like style transfer, without explicitly training for it. Thank you.
Image painting with learnable feature imputation. We propose a generative adversarial network for image painting. Our three main contributions significantly stabilizes adversarial training, leading to visually pleasing results. Our model is the first to be optimized exclusively on adversarial loss, where no handcrafted objectives are used. We propose a new method to handle missing values in image painting. Applying a convolution on top of a region with missing values is primarily undefined. The standard way of handling this is with zero imputation, or normalizing the output. Instead, we propose to replace missing values with the expected value determined by spatially closed pixels. Looking at our baseline network, we observe significant improvement when we replace all standard convolutions with our imputed convolution. From our qualitative results, we show state-of-the-art in paintings for large missing regions. Please see our paper for more details.
In this work, we present 4 seasons, a cross-season dataset for multi-weather SLAM in autonomous driving. Existing datasets for autonomous driving have been an important factor for advancing the state-of-the-art in many computer vision algorithms. However, in terms of benchmarking long-term visual localization, these datasets are typically limited. To overcome these limitations, we feature conditional changes by providing multiple traverses of the same route. This results in large appearance variations caused by changes in weather and seasons. We do not only provide multiple traverses of the same route, however, we also provide large variations in the environment. Our main contribution is a cross-season and multi-weather dataset, which covers both diversity and complexity in the environment. Moreover, we provide up to centimeter accurate georeferenced 6 degree of freedom poses. For more information, please visit our webpage.
Hi, this is a teaser for our paper Inline Double Layer Depth Estimation with Transparent Materials. In this paper, we present a robust method to compute smooth double layer depth estimates for scenes with non-Lambertian surfaces. Based on an industrial inline inspection system, we acquire 3D light field data of an object of interest. As an example, the acquisition on the right shows some opaque objects inside a clear plastic bag. From such light field data, we compute initial depth estimates from different structure tensor models and combine them in a cost volume. Subsequently, we extract and refine our results through a novel joint variational method to obtain consistent double layer estimates. For further examples and details, feel free to check out our paper.
Hi everyone. In our contribution, we would like to discuss the idea of incorporating the distance transform into deep learning architectures for regularization purposes to improve the image segmentation quality. Particularly, we follow Karam et al.'s derivation of a convolutional distance transform and embed this differentiable approximation in a cascaded form into the learning pipeline. We use the distance transform to retrieve a shape representation of both segmentation prediction and ground truth, from which a regression loss can be formulated to regularize the training process. Being able to calculate the distance transform with a differentiable operation secures the gradient flow during backpropagation. In contrast to related work, in this contribution the distance transform does not need to be learned, but it can be applied directly. Thanks for your attention. We are looking forward to meeting you virtually on our Spotlight presentation during the conference.
We present the disentangling multimodal variational autoencoder, a multimodal generative model that disentangles modality-specific and shared factors in a self-supervised fashion. A multimodal generative model learns a joint distribution over a set of input modalities x1 up to xm, and ideally, it should be able to handle missing modalities for many-to-many inference and many-to-many conditional generation. Here's an overview of the proposed method. In a nutshell, it partitions latent space into shared and modality-specific subspaces and learns to disentangle these with suitable information-theoretic objectives. Empirically, we demonstrate improvements on existing benchmarks of our previous work, and additionally, our method is unique in that it allows sampling from modality-specific priors, keeping shared factors constant.
Hi, my name is Christian Fulšić and I will present our paper, Multimodal Semantic Forecasting based on Conditional Generation of Future Features. With our model, we aim to predict multiple meaningful semantic futures while observing 4 frames from the past. We think that this would be especially useful when forecasting unoccluded scenery and emerging motion. We do so by converting the base single-level feature-to-feature model into a conditional generative adversarial model. We also make use of moment reconstruction losses to combat mode collapse. We evaluate individual predictions obtained at half-resolution cityscapes. With MR1 loss, we observe better accuracy compared to unimodal baseline, while with MR2 loss, we achieve lower accuracy but much more diverse predictions. Our model is sometimes still hesitating to replace close and large objects. However, we observe diversity when looking at pillars, traffic poles, unoccluded spaces, and moving objects. Thank you for watching.
Normalizing flows are models for approximating distributions mu of x given samples. Training such a flow means building an invertible function t of x, which maps from mu to a Gaussian latent distribution. One popular architecture for building such invertible functions is the real NVP architecture. It is based on neural networks. In this work, we derive how a single isolated real NVP layer behaves when it is directly coupled to the loss. This helps understanding what each layer can contribute towards reducing the loss. And it's also the situation of the last layer in a deep flow. Here's what we show. A real NVP layer has two parts, a rotation Q and an affine transformation, tau. We derive the global minimum for tau, and the loss value at this minimum then depends strongly on the choice of the rotation Q. This, in turn, then allows us to optimally determine Q. These results can be used to train deep flows in a layer-wise manner, but we highlight the remaining gap between layer-wise and end-to-end training.
I'm Max, and I'm highlighting our work Semantic Bottlenecks, Quantifying and Improving Inspectability of Deep Representations. We identify three obstacles that make deep confidence hard to interpret. First, the information in intermediate layers is highly distributed across hundreds or thousands of channels, which secondly results in incoherent activation patterns that are not aligned with semantics meaningful to humans. And last but not least, there is no agreed upon metric to quantify a model's inspectability. In this work, we propose an extension module we call Semantic Bottleneck Layer that is straightforward to integrate into existing models and produces semantically meaningful representations despite a drastic reduction of channels and no classification impairment. To quantify and compare our models, we propose a new metric we coin AUIC. Measuring AUIC shows a fourfold improvement using our semantic bottleneck layers over the baseline. If you're interested, I welcome you to attend my talk. Our paper ID is 28.
I'd like to present our work on bias detection and prediction of mapping errors in camera calibration. Camera calibration is a precondition for many computer vision applications. However, it oftentimes remains hard to tell whether a calibration has achieved sufficient accuracy. We therefore present two novel methods to capture the fundamental error sources in camera calibration: systematic errors and remaining uncertainty. To quantify systematic errors, we introduce the bias ratio, which quantifies precisely which fraction of the reprojection error is caused by biases. To quantify the remaining uncertainty, we propose a way to propagate uncertainties into image space and predict the expected mapping error. This provides information about the precision that can be achieved based on a given dataset. Importantly, both measures are independent of the underlying camera model and therefore widely applicable. We hope to see you at the main session.
Hello everyone, I am Ramakrishna and this work is done in collaboration with Jan Achterholt and Jörg Stückler at the Max Planck Institute for Intelligent Systems and Michael Möller at the University of Siegen. In our paper, we use differentiable physics to learn the latent representation of video. In a supervised setting, we encode the video into physical states, predict the next states using physics engine, and minimize the loss over ground truth states. The main contribution of our paper is in a self-supervised setting, where we use spatial transformer networks to render the predicted states into reconstructions and minimize the loss over input images. This makes sure that the latent space is structured and physically meaningful. We conduct an observability analysis of physical parameters to infer mass and coefficient of friction in three different settings: system identification, supervised, and self-supervised. The learned physical parameters can be used for video prediction. The first frame of the 200-frame rollout is provided along with applied forces. We can see that the error buildup is small.